In the first video of this lecture, we gave a bunch of definitions related to generating sets of modules. And in this video, we'll give a number of examples. So let's start with the example where M is a Z module. So what is a Z module? It's nothing more than an abelian group. There's a unique action of Z that turns an abelian group into a Z module. It's the one where Z acts on elements by having them taking your module element and adding it to itself a bunch of times, or the same thing with its inverse. Okay, so what are the Z submodules of M? We talked about this before. These are just the subgroups of M. If you have an element A in your module, what is the cyclic submodule of M generated by A? It's everything of the form Z A. So it's all of the things that are of the form R times A, where R is an element of your ring and A is this one fixed element. This just is the cyclic subgroup of M generated by A. These are all of the cyclic submodules of M. It is not difficult to see that M is generated by A as a Z module if and only if M is generated by A as a group. So if you have a subset A, the submodule generated by A is always going to include all of the sums of elements of A with repetition. Like it will include the abelian group generated by the set A. But in general, the action of the ring R could get you a lot of other elements as well. What's special here is the action of elements of the ring Z doesn't give you any new elements of M that you didn't already have. So in the case of Z modules, everything carries over, everything matches up with the language we have already developed for what it means to be a cyclic subgroup, what it means to be generated by a subset as a group. All right, let's look at a more interesting example. Let's take R to be a ring with 1 and take the R module where M is equal to R. So it's a left module over itself. I've written left here just to emphasize that R doesn't necessarily have to be commutative. Well, this is a cyclic module. M is everything of the form something in the ring R times the one fixed element 1 in M. So it's important that our ring have a 1. It's the set of all things that are R times 1, where R goes through the elements of our ring. So no matter how complicated this ring is, this is a cyclic R module. What are the submodules of M when you think of M as a ring R, a left module over itself? They're exactly the left ideals of R. So what are the cyclic submodules? So this correspondence between submodules and ideals is something we've seen before, but cyclic is new. So what are the cyclic submodules? They're exactly the principal ideals of R. If you just look at what this definition means, it's exactly the things that are generated by one element, which are principal ideals of your ring. All right, so there is a special name for a certain kind of ring in which all of the ideals are principal ideals. I'll just say quickly, let's suppose that R is an integral domain. In that case, R is a PID if and only if every submodule of M is cyclic. What's going on here with this assumption that R is an integral domain? Being an integral domain is part of the definition of being a PID. So you could think about how to modify things if you want to make a more general statement where R is not necessarily an integral domain. But the idea is all of your submodules come from ideals. All of your cyclic submodules are your principal ideals. If all of your ideals are principal ideals, then all of your submodules are cyclic. Okay, I want to give an example that is a really good one to know, because this is a statement that sounds plausible that just isn't true. So you might think that if you have a finitely generated module, its submodules must also be finitely generated. But that is not true. And this setup gives a really good example of this, and this is one that you should remember. Submodules of a finitely generated module need not be finitely generated. So let's take R to be a polynomial ring over Q in infinitely many variables. Q adjoin x1, x2, and so on. And the trick is to take M to be R and think of it as an R module over itself. This is finitely generated. It's even cyclic. It's generated by the single element 1. All right, so what are the submodules? They're exactly the ideals in this ring. And if you take the ideal, which is a submodule, generated by x1, x2, all of these infinitely many variables, we have seen that this is not finitely generated as an ideal. This is not finitely generated as an ideal. It's not a finitely generated submodule. So the idea is that this ring, you take M equals R, this is generated by the single element 1 as an R module. And if you take any ideal that's not finitely generated, that will give you an example of a submodule of a finitely generated module that is not itself finitely generated. Let's give a few more examples. Let's take I to be the ideal generated by 1 plus 2i in Z adjoin I. I is an abelian group, and it's also an ideal in this ring Z adjoin I. So it's both a Z module and a Z adjoin I module. It's a cyclic Z adjoin I module. Why? Because it's the set of all things that are of the form Z to the I times 1 plus 2i. It is this cyclic submodule of Z adjoin I generated by this element. It's all the things of the form something in Z adjoin I times this one fixed element, 1 plus 2i. What about a generating set of this ideal of this abelian group as a Z module? Well, it's generated by 1 plus 2i and I times 1 plus 2i as a Z module. Why is that? Well, what is it? What's really in this ideal? It's all the things of the form alpha times 1 plus 2i, where alpha is in Z adjoin I. Let's just rewrite alpha as a plus bi, where a and b are integers. So you can expand and think of this as the set of everything that can be written as a times 1 plus 2i plus b times I times 1 plus 2i, where a and b are integers. So this is a generating set of this Z module of size 2. It's not difficult to see that there's no generating set of I of size 1 as a Z module. Okay, so this is cyclic as a Z adjoin I module, and it's not cyclic as a Z module. Let's give one last example in this video. R adjoin X, the polynomial ring, is an R module. We know how the ring R acts on polynomials. And it has a spanning set, 1x, x squared, x cubed, all the powers of x. It has this spanning set that is infinite. So you have to be careful when you have an infinite spanning set, because you have these infinitely many elements, but you're looking at the set of R linear combinations of finitely many of this infinite set of elements. But here it's okay, because every polynomial in R adjoin X is an R linear combination of finitely many powers of X. There are infinitely many powers of X in this spanning set, but every polynomial can be written as a finite linear combination of this infinite set. R adjoin X is not finitely generated as an R module. Let me first say it's not enough to show that this spanning set doesn't have a finite subset that spans R adjoin X. You really have to show that there's no finite subset of R adjoin X that spans R adjoin X as an R module. Okay, well, suppose we did have such a finite spanning set. We had, suppose we just had finitely many elements, F1 up through Fk in R bracket X. Let's take the maximum degree and call that n. So the maximum of all these degrees, each polynomial has a degree. Take the largest one. And if you just look at what happens when you take this R submodule of R bracket X spanned by this set A, well, that just is R times F1 plus R times F2 plus R times Fk. We're taking linear combinations of these elements with coefficients in R. Those are polynomials of degree 0. You take R, some ring element, times F1, and you're getting either 0 or something that has the same degree as F1, or at least the degree doesn't go up, right? You have some issues if R is not an integral domain. But the degree can't go up. There are no polynomials of degree larger than n in this module. So what that means is that RA is not equal to this whole polynomial ring, because the polynomial ring contains polynomials of arbitrarily high degree. So this is a really nice example of an R module that is not finitely generated. Okay, but this is also a nice place to illustrate that the same set can be an R module for different rings. R bracket x is cyclic as an R bracket x module. So it's not finitely generated as an R module, but it's cyclic as an R bracket x module. Why? Because R bracket x is everything of the form something in R bracket x times the one fixed polynomial 1.